everyone, Larry Wynn here, your trainer for this on-demand virtual training course on the Philips Epiq ultrasound systems. And, first and foremost, if you haven't worked with us before, warm welcome to the Summit Imaging family. We're looking forward to working with you. And some general topics we're going to be covering in this training is, who is Summit Imaging, some general ultrasound basics and physics and how it works, image quality, which is the ultimate priority of all the equipment here, why it's so important, system disassembly, reverse those process, the process that we're taking you through to install, and as we're going through that, what the common faults are for the parts and what to look for, the transducers, what the common failures are on those transducers, especially on image quality and some voltage errors we're going to cover, and then at the end we're going to cover how these transducers get damaged accidentally, and giving you some information on what to look out for during the entire life cycle of a transducer to prevent that damage out there to lower your total cost of ownership. So, we hope you enjoy this content. The goal here is for you to service your own equipment. And if you have any questions during this training, please don't hesitate to reach out to us. Our tech support is available 24/7. Our phone number is 866-586-3744, or just email us at techsupport@mysummitimaging.com, and we can actually answer questions on the fly if you don't want to wait for the Q&A. There is going to be Q&A. We do have a lot of times for that, so jot down your notes, jot down your questions, and we can meet during those times to answer those questions there if you don't feel a need that you need an immediate answer right away. Training here is going to be about 3.5 hours, so we look forward to speaking with you in person, and we really hope you enjoy this training course. Just jumping into a little bit about us before we get started with our training. Summit Imaging, we are a technology-enabled service organization, and what that really means is we provide electronic repairs on ultrasound equipment specifically for now to repair your equipment out there in the HTM field to restore the failing equipment that you have on site, and you can fix it yourself to bring that equipment up and going and continue to care for patients. This is all rooted in our ability to repair down to the component level. So what we do with all the equipment that we have in the facility that we have revolves around us taking failing equipment, identifying and diagnosing the component or components electronically that are failing, making the proper repairs to the equipment, and then restoring its performance so you can get back up and running as quickly as possible. We've been doing this for since 2006, for over 14 years. We're in 32,000 square feet with state-of-the-art equipment that allows us to diagnose all these electronics. And we're just outside of Seattle, Washington, and Woodinville. We're in wine country, so if you ever want to visit us, it's a really good time to spend a weekend taking the sights. It's beautiful, and being wine country, if you like wine, this is a great place to be. So how do we really help HTMs out there? Well, we have awesome technical support. Our technical support is 93% accurate on the first diagnosis. This all revolves around an ecosystem of data that we collect of failures with our customers. And we actually are able to identify and diagnose and help HTMs in the field over the telephone, over text, over email, any way that you can contact us, with a lot of symptoms and error codes. We can help you diagnose down to the part, 93% of the time, on the first try, what's wrong with it. And it's also quick, so it doesn't take up a lot of your day. We really focused on compressing that time for HTMs to move on to the next diagnosis. I mean, the HTM, that position is so complicated by virtue of just all of the different types of equipment you're required to work on. And so we want to make it quick and easy to make your time as efficient as possible to be able to service and repair these ultrasound systems. We're responsive to, we typically answer within 3 rings. We are available 24/7 for you. And when you do need a part or a probe, 98% of the time, our products last beyond the warranty, and our warranty is 6 months. And in addition to that, like you're here today, training. We want to train you because you are the boots on the ground that's actually in front of the machine servicing the equipment, and we are in your back pocket as technical support to help you along the way, and really accelerating that diagnostic process of failing equipment together to get that equipment up as quickly as possible for your patients. At Summit Imaging, we're really focused on helping HTMs service and repair their ultrasound equipment. And the main ways that we do it is transducer replacements and repairs for you. Our repairs, they're free evaluations, so you can send them in, expect an evaluation within 24 hours of receipt of your transducer. Replacement parts. If your system is failing at a hardware level, we're able to deliver you replacement parts the next day. And again, our 24-hour technical support is invaluable to HTMs out there because you don't work on ultrasound all the time. This expertise that you have at your fingertips, it just allows for an extraordinary acceleration of diagnostics and accuracy to really minimize and decrease that system downtime. And then hands-on training. Obviously this training is a virtual on-demand training, but when the time comes, we love to have our customers come out here and we train you in person, get hands-on with the machines to diagnose these things quickly and to get them up and going. And because we're all remote support, like I said, via text, phone, email, whatever you're comfortable with, we're just able to ship anywhere in North America. So that just makes us a great solution for HTMs that are, currently or deciding to, service and repair your own assets and ultrasound equipment. Geography is, we're only limited to where we can ship to. Well, let's jump into it. What is ultrasound? Ultrasound is technology that uses sound waves to create an image. And so if you're looking at an ultrasound system and the probes and the whole ecosystem of the technology, this actually generates diagnostic images to help patients. And why is ultrasound not only popular, but rapidly growing because there's been new uses for it consistently because of a few different reasons. Number one, non-invasive. A patient just simply needs to show up and we turn on the machine and put some gel on and you're off to the races and you're scanning already. There's really no prep needed. It's immediate. So, as fast as you can turn on the machine and the patient can arrive, you're actually scanning, that quickly. Like I said, the applications of ultrasound is growing at a rapid pace, being used in, joints and, athletics and, beyond the standard and traditional applications of ultrasound. And now with technology, the hardware being able to do so much more, the portable ultrasound units are now providing a level of diagnostic image quality that allows ultrasound to travel to patients now instead of arriving to a lab. So it's just a great technology. It's growing, and we fully expect the install base to continue to rapidly grow because the resolution is getting better, the response time is getting better. It's a live image, and as these doctors are figuring out how to get these images for diagnostics that are outside the traditional scanning properties, it's just going to help accelerate the use and the application of this technology. All right, and so this slide, ultrasound technology. There's a lot of interchangeable terms, and we just wanted to start off with, you have an ultrasound system, you have ultrasound transducers. Those two things combined create a diagnostic image. And this is what we wanted to start off with because the ultrasound system and transducers absolutely rely on each other. And once connected, act really as one unit. And that's an important concept to start with because when we start talking about failures in the later slides of this training, many faults and failures can be the same on your screen for a sonographer or for you, and the errors could be similar or absolutely the same, but you don't know if it's the ultrasound system and transducers. So, this is important that, if you have image quality issues, especially that, don't just assume it's the transducer right away. It could absolutely be the system itself. And so the concept here to really drive home is the ultrasound system and the probes work together. And if one is failing, it will impact the quality of your diagnostic image. Okay, some light physics work here. Sound waves will generate information if the sound waves bounce back off of a surface and return back. And so the idea here is that, the system, the ultrasound system itself that we just saw, will actually send power to the transducer. The transducer has a crystal that vibrates. It will send sound, and then it listens to see if any sound waves are returning. And if it does, then it takes that information and it processes it and it generates an image. And so what you can see here, the wave is originally sent, then it goes into a listening mode where the reflection comes back. If there is no reflection, there will be no information. But if there is a reflection, then that data will be compiled by the processing unit to generate an image that you will see on the screen. And now let's talk about the Doppler effect. Now that we know that a crystal will send and receive sound, ultrasound, the huge benefit is that it's a live image and it's not invasive. And so for a sonographer, a physician, to see a live image, in addition to knowing, direction of blood flow, all these different aspects of ultrasound are incredibly valuable. But it's important that this information, to be a live image, to see exactly what's going on inside the body, is the Doppler effect. And so the concept here is that when an object is reflecting ultrasound waves, it changes the frequency of the reflected echo. So if there's a higher frequency, it's moving towards the probe. So, for example, blood flow, it is referred to as, is it going towards the transducer face or is it going away? And this Doppler effect is saying that if it's coming towards the probe, like this truck here is moving in this direction, this person on the right will actually hear the frequency getting higher, as the person to the left over here would actually see, or not see, but hear the frequency getting lower as it's going away. And in ultrasound, you can see that. It takes all that information and it puts it in this image that you can see on the monitor. And so the frequency is really important to identify direction of possibly blood flow in this particular example. And another physics aspect that we have to chat about is how frequency impacts resolution and penetration of the image itself from the type of transducer it is. So in general, the lower the frequency, the deeper the penetration you can get to scan in the human body. The lower the resolution. The higher the frequency of the transducer, the lower the penetration, but the higher the resolution. So there's this constant give and take in all these probes, and that's why you have so many different types of probes for specific applications, because there's different beam forming techniques, but specifically around frequency, if you are scanning your carotid, you need a very high resolution, very near field or low penetration transducer, like an L12-3, or If you need to scan, your liver or your diaphragm, that would be a C5.1. So the L12.3 being more the carotid, 12 to 3 megahertz. So 12 megahertz is pretty high, and a C5.1 maxes out at 1 megahertz on one side, which is a very low frequency, allowing it to really penetrate through all the tissue to see the organs, that are pretty deep inside, relative to more of a superficial scan like a carotid. And with that quick crash course on the physics of ultrasound, uh, in all, at the end of the day, it's sound that is sent, whatever data is reflected. The ultrasound machine is a phenomenal piece of technology that will compile all that information into a live image and gives us diagnostic information on the patient without being invasive. Turn on the machine and begin scanning the patient, and that's just an extraordinarily powerful technology in healthcare, and the reason why the downtime is so critical. These ultrasound machines are becoming heavily used, and now that they're heavily used, the downtime, it just becomes so costly for healthcare facilities. So this amazing technology continues to evolve, and we are here to help you repair and service your own equipment to minimize that downtime. Okay, what is an ultrasound system? The ultrasound system referred to sometimes the system, the box, the console. This is the piece of the ultrasound technology that really does all of the work with the information the transducer receives as far as the sound data is concerned. And it does all the processing and puts it on the screen. And it also allows for the user to manipulate the transducer. It can change the frequencies, the depth, the gain, and a variety of different things to be specific to obtain the best image possible of the patient on what they're specifically looking for. So the ultrasound system controls all of this and is really the central processing unit of the entire technology. Within ultrasound systems, there's typically a specialty, and in today's training, we're really focused on the Epiq 5 and 7 platforms. And now there's actually different versions of them that are specific to the type of imaging needs a user would specialize in. And in this particular case, there's a general type of machine, a women's machine, and a cardiac machine. And this will be denoted in either Epiq 5 or 7 prefix, but the letter on the end will tell you what specificity and specialty that equipment can run. And so Epiq 7G stands for just general imaging. Epiq 7W would be women's, which used to be called OB, and then Epiq 7C for cardiac. And now you can change that prefix. I use Epiq 7 as an example, but that could be Epiq 5 as well. But generally, ultrasound systems are broken into specialties. Now, there are some shared service machines out there, and a little fun factoid, Siemens was the first one to do that, where it didn't have really a specialty. It could do multiple. But in generalities here, it is typically broken out by these different applications because they use different transducers oftentimes. There are some transducers that actually are cross-platforms to the GC and the W, but there are some specific transducers and specific applications to be specialists in each one of these sectors. Now, what are the different transducer types and applications? We're going to review a few here. There's more, but these are the general ones, and it all depends on how it sends and receives sound. And so we call that different types of beamforming. And so as you can see, in the linear transducers, it's very linear from one side to the other, where it will fire each called element or channel in a linear fashion, and it's actually a linear probe, or linear face. So we'll fire 1, 2, 3, 4, and it'll step across, and it'll actually compile all of those individual channels or elements together to create an entire image. Now, convex, you can see the characteristic is a curve. So this allows for, a wider field of range and some more penetration that, we kind of talked about the C51 earlier. That would be a curved, which the C stands for curved, and the 5 to 1 megahertz, so C5-1. So the vernacular of the model of the probe is really, is it what kind of crystal is it? Is it a linear or convex? And then the frequency range. And then at the end, you have a sector transducer where it actually beamforms straight out of the center. And basically what this is doing is, instead of going from one channel to the next and stepping across, it will actually image in sectors. So if you were looking at an ultrasound image down here, and this is what a sonographer would see, it would actually image this section here, then it would take the next sector, and the next sector, and the next sector, and so on and so forth, and then would compile those sectors together to make an image. And so you're going to see, as we kind of step through, you might see some sector probes actually have a little bit different failures relative to the more traditional linear or convex, but in reality they all are based around how they can transmit sound in the beamforming. And some examples, for general, you would have a linear 9 to 3 megahertz and a C51 over here. Women's specifically would be some transvaginal transducers, so you have a C10-3V. C stands for, it's a convex 10 to 3 megahertz vaginal probe, or an older version is a C8-4V convex 8 to 4 vaginal probe, inner cavity. And just from personal experience on being a father, those are pretty incredible probes, super high resolution. If you can see a fetus when it's a rice grain, you can see the heart beating. I mean, it's so small, and the ability for ultrasound to see that at that early of a stage is incredible. And so, yeah, just I think we have all been impacted by ultrasound in one way or another. If not yet, you will in the future, because it's just so widely used and so powerful. And then for cardiac, you have some specific probes, X72T, which is a T probe specific. We'll get into that later. And an X51. This is a a matrix sector probe essentially. So it's a sector probe, 5 to 1 megahertz. And sector, you're going to ask, well, why is that beamforming different than the rest? Well, it's designed that way because a main purpose of that is to actually scan the heart without having to go inside the esophagus to get a clear shot of the heart. And so with ultrasound, it cannot travel through bone. It's too hard. So ultrasounds are very good at identifying soft tissue and the different densities of soft tissue, and you'll see that on your image on the different densities. However, to get to the heart to see all 4 chambers, the sector probe, the surface area of it is 1 by 1.5, and that's designed to actually shoot through your ribs, so you can go in between your ribs and shoot in to actually see the heart as best as you can without actually going inside the body.